topic of Module 7 is alkenes. This should be a somewhat easier module because we have emphasized a lot of structure and bonding early in the course, and we've seen plenty about alkenes before. If you recall the bonding and structure of alkenes, they are trigonal planar geometry, meaning ideally all the bond angles are 120 degrees. The sigma bond framework is sp2 hybridized, meaning each carbon has an sp2 hybrid here, here, and here. 3 sp2 hybrids, leaving that leftover p orbital, if you remember, above and below, which then overlaps with the other carbon's p orbital, creating this pi bond above and below with 2 electrons in it. In our next unit, the reactions of alkenes, we will see how those 2 electrons can engage in reactions, just like we've learned any 2 electrons contained in a bond, if it's set up right, or in a lone pair, can form bonds. So the structure and bonding of alkenes dictates their activity and reactivity. The pi bond stops rotation around this double bond. So you cannot rotate here like you would with single bonds. However, if the pi bond is broken, then the alkene can rotate. In fact, a better way to say it is, in order to rotate around a double bond, you have to break the pi bond. So if you look at these pictures here, like this, ignoring the colors, this pi bond here has been formed because it's in plane. It has to be in plane to form and to maintain itself. These look a little funny on both sides to me. So if you're able to break that bond, then you can rotate. Notice if you rotate, there's no more overlap. In other words, you don't have a pi bond. So here they are at 90 degrees. In order to do that, often you can subject a compound with double bonds like this with UV light. In fact, we do this in one of our experiments in Organic 2 Lab. Sometimes you'll see this just written as that, HNu. So this is maybe a little bit better picture. You can see the trigonal planar geometry here, the overlap, and then the breaking of the pi bond, which if you can imagine the continued rotation around there. So off to the right here, we see cis, this molecule, cis stilbene, which is a common name. This is what we make in Organic 2 Lab. Actually, we make this one down here, and we get a little bit of this one produced as well. But the equilibrium favors the trans stilbene. And the reason for that is also structural, because the cis stilbene has quite a lot of steric strain. So these big groups, when it's cis, will be literally bumping into each other if you build the model. If you look at even a compound like this below, which we would call a butene, because it's got 4 carbons, these bond angles here are actually pushed out to about 127 degrees because of this steric strain, even with just 2 methyls. Whereas the bond angles for the trans are your classic 120 degrees. So sterics play an important role in structure and reactivity sometimes. We need new descriptions for the stereochemistry of alkenes rather than cis and trans. Cis and trans becomes ambiguous at some point. For example, here we have your alkene with 4 different things around it. if I was to call this cis, what am I referring to? Am I referring to the two methyls? Or am I referring to the methyl or the ethyl and the proton? So it's not clear. If someone tells you cis for this molecule, you wouldn't know exactly how to draw it. There'd be two different possibilities. So we need a clearer nomenclature. That's the EZ nomenclature. So the EZ nomenclature is based on priority groups in the same way as R and S nomenclature. So same priority rules. As RS nomenclature. And the difference is you don't have to do 4 groups because these are not chiral molecules, right? You look at each carbon. So if we look at the carbon on the left and prioritize the 2 groups attached to it on that side of the alkene. So you're taking sides here. The ethyl group would be priority 1 and the methyl group would be priority 2 using those same priority rules. Then you go over to the other carbon and assign the methyl 1 and the proton 2, lowest value. Now what you do is look at how you get from 1 to 1. And if you look at the orange here, going from 1 to 1, and you imagine a middle here, it kind of looks like the letter E turned on its back. If it looks like E, this is the mnemonic. Then it's Z, stereochemistry. And if it looks like Z, it's E. Other people have different ways to remember it. Z sounds a little bit more like cis, perhaps. Some people remember that. So let's look at this example on the right. This carbon here, priority groups 1, 2. Priority groups 1, the isopropyl 2. From 1 to 1 looks like Z, so it's E. And this one over here to the left is Z, right? Let's do a few more examples. We have here this carbon. Now, immediately you see these are the same. So in a case like this, which happens pretty often, there is no cis or trans, there's no E or Z. There's no other version of this molecule, basically. If you switch these two, the molecule stays the same, if you notice. This molecule here, with the ring, you can't really describe it as cis, although, yeah, you really can't. You could assign EZ to this, but you don't really have to. Notice the name, 1-methyl-cyclohexene. There's really no other way to draw 1-methyl-cyclohexene. So the rings, are always constrained in that way. So you don't really need EZ nomenclature for this. Remember, the whole point of nomenclature is to be unambiguous. And if there's only one way to draw 1-methyl-cyclohexene, then there's only one way to draw it. So notice in the naming, we number through the alkene, and here we put the methyl group at position 1, where the substituent is. So going into the nomenclature a little bit more, you look for the parent chain of the molecule, the longest chain that contains the alkene. And then you number through the alkene. So 1, 2, 3, 4, 5, 6. So it's a hexene. And you need the ene, not ane, right? Hexane, hexene, very specific. And then we have a methyl group at 3, so it's 3-methyl 1, squeeze that in there, 1-hexene. Because you have to say where the alkene is in the chain, 1-hexene. And like the example we saw above, there's no cis-trans EZ on the double bond. So that's the name, complete name. We have here a cyclohexene. And do we call this 1-methyl 2-cyclohexene or 1-methyl cyclo 2-hexene? Well, remember we number through the double bond, so 1, 2, 3, so it's 3-methyl cyclohexene is sufficient for that. Look for the parent chain containing the alkene. Here, if you don't, you'll have a longer chain. But the parent chain containing the alkene is a 1, 2, 3, 4, 5, 6, 7. It's a 1-heptene. And remembering from way back, that's a sec-butyl group at position 2, so it's 2-sec-butyl 1-heptene. How about this one? 1, 2, 3, 4, 5, 6, and then checking. If you numbered it in the other direction, 1, 2, 3, it's the same. So it's the same either direction you go. 1, 2, 3, 4, 5, 6. It's a hexene. It's a 3-hexene. But we have to define the stereochemistry here. Trans or looks like Z, so it's E. The EZ is probably preferable. Continuing on. When we have 2 double bonds in the same chain like this, it's a diene. So 1, 2, 3, 4, 5, 6 puts the 2 enes at starting at 1 and 4 rather than at 2 and 5 if you numbered in the other direction. So this is a 1, 4, 1, 2, 3, 4, 5, 6 hexadiene. Diene. Hexa, 6 diene at 1 and 4. And there's a E or Z stereochemistry here. Looks like Z, so it's E, so it's E14 hexadiene. And you don't really have to define the alkene at 1 because it doesn't have, further because it doesn't need it. It doesn't have E or Z. What about this one? It's a butene. 1, 2, 3, 4. It's 2-butene for the parent molecule. It's got a fluorine at carbon 2. So it's 2-fluoro, F-L-U-O-R-O. 2-fluoro, 2-butene. And we have to define EZ here. So priority groups. 1, 2, 1, 2. From 1 to 1 looks like E, so it's Z. Z2-fluoro-2-butene. This is a cyclobutene. There isn't really any need to say exactly, well, in this case there is. So numbering through the double bond in either direction, 1, 2, 3, 4. In the other direction is no different as far as where the methyls are. So it's a 3,4-dimethyl cyclobutene, but here you need the cis trans, not easy, because one of the methyls is up and the other is down, so they're trans. Excuse me. Trans 3,4-dimethyl cyclobutene describes that. Here's another molecule that has trans groups on it. It's a cyclohexene. Always start with the parent name first. Cyclohexene. Giving these substituents the lowest combination of numbers, 3, 4, 5, starting from 1, 2 in the alkene, rather than if we started numbering here, for example, that would be 1, 2, 3, 4 for the propyl group, 5, 6 for the methyl group, so 4, 6 rather than 3, 5. 3, 5 is a lower combination of numbers, right? So this is a 3-methyl 5N-propyl. 3-methyl 5N-propyl, normal propyl, that's what the N is, cyclohexene, and it's trans. So that's the full name. Trans 3-methyl 5N-propyl cyclohexene. Here's another diene. 1, 2, 3, 4, 5. It's a pentadiene. And it's a 1,3 pentadiene. And it's cis or Z at the 3,4 alkene. Just briefly mentioning some alkynes, we have ethyne, so alkynes have the -ine suffix, common name acetylene, which doesn't really make any sense in any naming sense. But that's acetylene, like what's used in acetylene torches. This is a propene, right? A propine, excuse me. 1 propine. This is a butine, 2 butine. This molecule I've already drawn here, oct 1-ene 4-ine. Sometimes the naming gets a little silly. 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. Note that there's carbons there. So it's an octine. It's an octine, but it's got an ene in it. So it's at 1 ene, 4-ine. And notice how I've drawn this linear. Don't ever forget that alkynes are linear. This is the same thing drawn like I've seen it often, unfortunately. And do not draw it like that. It's not trigonal plane or like a double bond. It's linear. SP hybridized linear geometry. Excuse me. Okay, that's that longish video. Actually, this is the only video on alkenes.